Welcome to Maths with EJD. In this video, we are focused on least squares approximation for overdetermined equations. In the last video, we've talked about least squares approximation for linear fitting, and we saw how we could actually fit a line to a set of given points, and we discovered the calculation can be quite lengthy, although the Python code really helps to do things faster. So here, we are using the same least squares approximation method for taking care of this kind of equation. And our objective is basically to understand how to solve overdetermined systems of linear equations using the least squares method. Now, overdetermined system is a system where where you have more equations than you have unknowns, and that's normally you're not supposed to get a correct a proper answer with that, but least squares approximation can actually help to get some approximate solution to the problem. So, this lesson covers the process of finding an approximate solution when the number of equations actually exceeds the number of unknowns. So let's talk about the introduction. Because this is not our first time of coming across least squares approximation. Of course, the procedure to undertake each one is a bit different. So line fitting is that one, and this is for overdetermined system. And an overdetermined system, or an overdetermined equation, an overdetermined system is a system of linear equations where there are more equations than unknowns. Okay, you have more equations than you have unknowns. Maybe you have 3 equations and you're looking for 2 variables. That's a very good example. In such cases, the system may not have an exact solution. So you can have groups of solutions, right? However, the least squares method provides the best approximation by minimizing the sum of the squared residuals, Okay. So consider the system AX equals B, where A is an M by N matrix. Of course, making sure that M is greater than N. That's what guarantees that the number of equations is higher than the number of variables. Then X is the N by 1 vector of unknowns. N by 1 vector. So X is the N by 1 vector of unknowns. So I'm going to see very soon. Then we have B. B is the M by 1 vector of known values. Okay. So the goal is to find the solution. I want to find the solution that minimizes the error J of X equals the absolute value of AX minus B all squared. Okay, So we want to minimize this error. That's basically the idea. So just like in the case of linear line fitting too, it's also, we are minimizing the least squared errors. That's the residuals. Okay. So the least squares solution, the least squares solution is obtained by solving the normal equations, we started with ax equals b, right? So imagine that you have, so there's now A transpose A of x equals A transpose B. So you do left multiplication with the transpose of A, and that way you can minimize. And just like in the case of line fitting, right? So you can say this gives the best fit, solution. It gives the best fit solution to the overdetermined system, Okay. So, I mean, it's a very powerful method to take care of a problem like this. So let's look at an example, as we always want to do. So consider the following system of equations. So you have x1 plus 2x2 equals 5. Then you have 2x1 plus 3x2 equals 6. And then you have 3x1 plus 4x2 equals 7. Okay. Now you see we have three equations, but two variables. Three equations, two unknowns. So this is clearly an overdetermined system, right? So consider the following system of equations. Then find x1 and x2. Find x1 and x2. Okay, that's all we need. So solution, the system is clearly an overdetermined one. It's clearly an overdetermined one, since the number of equations, which is 3, is higher than the number of unknowns. The number of unknowns, that is 2. Okay. So as a result of that, we know least squares method will be a very nice method to use. In this situation, we adopt the least squares approximation method. Okay. So first, we represent the system as a matrix. So that means we have, so if you look at the system now, we have 1, 2, 2, 3, 3, 4, 5, 6, 7. Okay. 1, 2, 2, 3, 3, 4 into x1, x2, and all of that is equal to 5, 6, and 7. 5, 6, 7. So from the normal setup, right? So it means this is we have A to be 1, 2, 2, 3, 3, 4. Then that X now is our X1, X2, and B is 5, 6, 7, like that. So what do we do? So we know that, I mean, we already know what to do, right? We know we need to find X using A transpose A X, A transpose AX equals A transpose B. So now this is A now. A is 1, 2, 3, 3, 4. So transpose A transpose now. So it's a 3 by 2 matrix. It becomes a 2 by 3 matrix when we transpose it. So that means row 1, which is 1, 2, becomes column 1. So this is 1, 2. That's A transpose. 2, 3, which is row 2, becomes column 2. Then 3, 4, which is row 3, becomes column 3. So don't forget, this is 3, 4. This is 4. Okay. So that now multiplied by 1, 2, 2, 3, 3, 4. And okay, then we have that beside X, which is X1, X2. And that is equal to 1, 2, 2, 3, 3, 4. 1, 2, 2, 3, 3, 4 into 5, 6, 7. So we can do that. So I move on to say now that this is, so we take care of this first. And, we start from the one on the right-hand side, one to the A itself. So don't forget, this is A transpose, this is A, this is X, this is A transpose, and this is B. That's what we need. So the one on the right-hand side, right? Because we have two rows here, we write each row twice. Okay. So we have 1, 2, 3, 1, 2, 3, then 2, 3, 4, 2, 3, 4. And again, so for the first rows now, we have 1, 2, 3 on each side. So this is 1, 2, 3, and 1, 2, 3. And down, we have 2, 3, 4, and 2, 3, 4. So that's that here. And that is into X1, X2. Of course, we already expect that a 2 by 3, if you multiply a 2 by 3 matrix by a 3 by 2 matrix, so this will go and you end up having a 2 by 2 matrix. So that gels with the fact that the X is a 2 by 1 column matrix. So that is equal to, again. So because 5, 6, 7 is 5, we have 5, 6, 7, right? A transpose B. A transpose B. What do we do for that? So we have a 3 by 2 by it's the transpose we need. Yeah, I was already wondering how this is going to happen. Okay, we need the transpose, not the A itself. So this is 1, 2, 2, 3, 3, 4. Okay, this is the only way it can work. 5, 6, 7. Okay, the transpose is 5, 6, 7. So this is A transpose B. So this is the only way it can work. You have a 2 by 3 matrix multiplied by a 3 by 1 matrix. So we are going to get a 2 by 1 matrix at the end of the day. So if you want to know more about matrices, I have a whole playlist on matrices. My first playlist on this channel is on matrices, so you can check that. Several videos to dissect every aspect. So so we have 1, 2, 2, 3, 3, 4, like that, into 5, 6, 7, which works. Very good. Okay, yeah, we can go straight now. So because we have two rows, we write the right hand side twice. We have yeah, so we have two rows here. So we write 5, 6, 7 twice and invert those ones over it. So 5, 6, 7, 5, 6, 7. And the first one you have 1, 2, 3, and then you have 2, 3, 4. So we end up having a 2 by 1 matrix. So let's do the computations. So this is 1 plus 4, that's 5. 1 times 1 is 1. 2 times 2 is 4. 3 times 3 is 9. 9 plus 4, 13 plus 1, that's 14. So we have 14 for this one. And for the next one, 2 times 1 is 2. 3 times 2, 6. 4 times 3, 12. So 12 plus 6 is 18. 18 plus 2 is 20. Okay, so this is 20. Next one, we have 1 times 2, 2. So 12 plus 6 plus 2, that's still 20. And then we have, okay, 4 plus 9 plus 16. 4 plus 9 is 13. 13 plus 16 is 29. So we have 29. So all this done. So we have this now into x1, x2, and that is equal to, for the other side now, 5 times 1, that's 5 plus 12, 17. 17 plus 21, that is 33, right? I mean 38. 5 plus times 1, 5. 6 times 2, 12, that's 17. 17 plus 21, that's 38. So that's 38. And down here we have 5 times 2, 10, plus 18, that's 28, plus 28, that's 56. So this is the new system we have. So it's looking great now. So we can go further and still have, so we now need to expand further at this side now. So again, we have 2 rows here. So we write x1 twice. So we have x1, x2, x1, x2. So that means we have 14, 20, and this is 20, 29. So all of this now is equal to 38, 56. Okay. 38, 56. So if you do this, this is so this one now is 14x1 plus 20x2 is equal to 38. And then for the next one, this now, bring it down. This is 20x1 plus 29x2 is equal to 56. So we have a beautiful system that looks solvable, and we can deal with that right now. So what do? Call this star, like I always like to do, and then so let me go for something else now. Let me go for, okay, let me go back here. So call this star and call this star star, if you like. So for star now, I want to multiply star by 20. So I can multiply star star by 14. I multiply star star by 14. The reason is that if I multiply this by 20, I multiply this by 14, they'll become the same. So I can easily eliminate x1. So 20 times 14 is 280 x1. 20 times 20 is 400 x2. Then 38 times 20 is 760. Then 14 times 20 is 280 x1. So they are the same. So we can easily delete those. 29 times 14 is 406 x2. And that is equal to 56 times 14, that's 784. 784. So now we can subtract. So we can say, so subtracting, okay, subtracting. So 280x1 cancels 280x1. Then 406x2 minus 400x2 is 6x2. 784 minus 760, that is actually 24. Okay, so we have 6x2. We have 6x2 divided by 6 equals 24 all over 6. So 6 cancels out. So we have x2 is equal to 4. So our x2 is 4. And since we have this, it's easy to now get any other one we want to get. So we can use the easier equation, which is equation x. So from x, so from star, from star, we have 14x1 plus 20x2 equals 38. So that means we have 14x1 plus 20 into x2. x2 is 4, and that is equal to 38. So we have 14x1 plus 80 equals 38. And then that's 14x1 equals 38 minus 80. So that means we have 14x1 equals minus 42. And then that is x1 is equal to, divide through by 14. That's what we are doing. 14x1 over 14 minus 42 divided by 14. So 14 cancels 14. So x1 is equal to minus 3 because minus 42 divided by 14 is minus 3. So what do we say? Therefore, um, therefore, the approximate solutions to the undetermined, to the overdetermined system, to the overdetermined system, to the overdetermined system of equations, to the overdetermined system of equations, using least squares approximation, is x1 equals minus 3 and x2 equals 4. Okay, that's the solution in this situation. And so we see the efficiency of the least squares approximation method in taking care of this. Of course, you can also present it as, say, x equals minus 3, 4, anyhow you want to do that. So we see that in overdetermined systems where there are more equations than unknowns, the least squares method finds the best approximation to the solution by minimizing the residual error. So we have the solution in this case. So this minimizes the sum of squared residuals and represents the best fit solution to the system of equations. And as I always like to do, I like you to see the Python implementation of this, which makes things faster. We spent some time doing this, so you could always extend it. So if I run this now, you just say x1 is minus 3, x2 is 4. So what if I want to add another layer to this? I mean, I just want to see if I want to cause trouble. Say I now say this is maybe another set. I now have 7, 11, and then the right hand side is now for this I say 12. If I run this, I mean, so we have an approximation still. So we have an approximation still, which is 1.56. X2 is 1.56. I mean, X1 is 1.56 and X2 is 0.24. Okay. So what if, okay, let me make that into, so since you know the answer already, so I want to make that as a practice question where you now have, say X1 plus 2X2 equals 5. And then you have 2X1 plus 3X2. Yeah. 2X1 plus 3X2 equals 6. Then you have 3X1 plus 4X2 equals 7. And lastly, you have 7X1 plus 11X2 equals 12. So this is an overdetermined system. You have 4 equations, but you need only 2 things. So let me return this to the original way it was. So we get our minus, something is wrong here. Okay, I've not completely removed this. So we get our something is wrong. What did I do? Oh, there's a parenthesis issue. Okay, yeah, I need this. Yeah, that's so you can see just a comma can cause all the troubles. So I go back and I give a practice question for you to try your hands. So practice question. Okay, you have an overdetermined system. I just say solve x1 plus 2x2 equals 5. Then 2x1 plus 3x2 equals 6. Then 3x1 plus 4x2 equals 7. Then 7x1, so this is what I'm adding now, plus 11x2 equals 12. Definitely the answer is not going to be minus 3 and 4 anymore because I've added another data point, so to speak. So it's going to be something different. So let me say this in the comment section, whether on YouTube or Facebook, feel free. And then, of course, you find the code on Facebook where you can even keep extending to see what the values look like. So if you have subscribed to this channel, thank you very much. If you have not, feel free to go ahead and subscribe right now. Hit the notification bell so you can always get alerted each time a new video is released. Comment with the answer to this practice question. Then you can just form questions for yourself and solve them using this method. Then, of course, let me know if there's a topic you'd like me to teach, or a problem you'd like me to solve. Then don't forget to like and share so that more people can have access to this great content. Till I come your way again, keep doing maths right. Bye.